Hello, and welcome to another video lecture for Machine Design ME372. In this video lecture, we're going to start talking about fatigue and fatigue analysis. And to start off, I'd like to show you this article that I found now several years ago, but it was posted in February of 2013. And what it is Honeywell Aerospace signed a deal to create what they call a HUMS, which is a condition-based CBM system that monitors the health and usage of an aircraft's drivetrain. So HUMS continuously checks aircraft health and usage by monitoring vibrations at numerous points throughout the drivetrain to pinpoint mechanical faults. It monitors up to 36 different elements, and it identifies signs of stress and fatigue before they become serious issues. And this was particularly valuable, they say, in the Middle East, where there's a lot of sandy, hot, dusty conditions. The HUMS have been used on thousands of commercial rotorcraft, including a wide variety of platforms from AgustaWestland, Sikorsky, Bell helicopter, Eurocopter, and MD helicopters. So that's quite a slew of great companies that make helicopters where this HUMS system has been applied. And Honeywell claims its HUMS products have helped U.S. Army Apache helicopters reduce mission aborts by 30%. To me, that number's huge. And by doing this online real-time monitoring of their drivetrain and other systems that see significant fatigue and wear, they are able to reduce the mission aborts. They've also reduced the maintenance test flights by 20% and scheduled maintenance by 5 to 10%. So as an engineer, I hope something like this would excite you. To me, I could for sure work for a company like Honeywell that is developing real-time monitoring systems that would monitor parts for fatigue and vibration and wear, and then send that to a remote server. One time I worked for a company called ABB, and what I did there was I developed a condition-based maintenance system, and a company in Idaho would monitor the robots used by a company in Canada. And when a bearing started to go bad or significant wear on a certain part was monitored and recorded real time by one of their robots, someone in Idaho would receive an alert, and they could then send that information to the company using the robots in the manufacturing process. So this idea of condition-based monitoring is a big thing in mechanical engineering, and it's becoming bigger and bigger, where we're able to real-time monitor and diagnose problems and then fix them a lot more quickly. So I hope this topic kind of excites you. Fatigue is a big area, and like bolts, we will follow the book very closely in this chapter. And again, like chapter 8, you will have this chapter 7 available to you on the exam. Excuse me, it's chapter 6 that is fatigue, not chapter 7. And you will have chapter 6 available. If we look at this image here, it's the image of a broken rotating shaft. And you've been asked as an expert engineer to try to diagnose what exactly happened in this failure problem. So some of the questions that you should ask are, was it fatigue or a static failure? Where did the failure initiate? Where did it finally break? Was the shaft under a high load or a low load, or can you tell? And can we tell which way the shaft was rotating? So if we look at this, we can see that here we have our circular shaft. This is the keyway, where a wedge is put in here that connects this shaft to another rotating part, and then as it spins the keyway. So the keyway is what connects this shaft to another rotating part. To look at whether this was a fatigue or a static failure, we can look at this surface and see that it was fatigue. And the reason why is because in a fatigue analysis, we get these striations, or what are commonly referred to as beach marks. And they're simply lines that you can see in the failure plane. And what happens in a fatigue analysis is a crack is initiated and then it propagates. And what happens is every time this shaft makes a cycle, that crack opens a little bit more and then closes. And each one of those openings causes one of these beach marks. So remember that fatigue is a two-step process. It's crack initiation followed by crack propagation. So if we can prevent the cracks from initiating, then they can't propagate, and we can improve the fatigue life of our parts. So we will look at another example on the following pages where we can see static versus fatigue more clearly. Where did the failure initiate? Well, we know that cracks need to be under tension to propagate. And so the crack to propagate needed to be under a tension load, opening the crack up. And right here in this keyway, we can see localized lines propagating in an outward direction, and those lines continue on, like shown here, until finally we come down to this part and have a brittle fracture. Now we know the crack didn't initiate here because this is a nice smooth surface and there wouldn't be a crack in this region. But up here in this notch where we have this sharp corner, that's where a crack would initiate. That sharp corner in that notch is almost a crack to begin with, and then it propagates and comes this way. Now we ask ourselves about the size of the load, and we can see that the fatigue failure had a propagation that came clear down until it reached this point here, and then it finally broke the shaft. So the load on this shaft was very small because it didn't have a brittle fracture until here. This much of the shaft was carrying the load. Whereas if we would have had a high load, it would have had a brittle fracture up in this region somewhere. Now we ask ourselves, which way was the shaft spinning? And this is a difficult question unless we know whether the shaft was being driven or whether the shaft was doing the driving. What we do know is that this corner had to be in tension. So if this shaft was doing the driving, it would have to be pushing on the member going this way, and the shaft would be spinning clockwise. That would put force against this part of the notch and push the notch open, creating tension down here and the propagation. That's again if the shaft was doing the driving. Now, if the shaft was being driven, if the shaft was being driven by another part that was mated onto here, then it would be getting pushed on. And to cause tension in here, we would have to push on this edge. That would cause tension. So if the shaft was being driven, it would be spinning in a counterclockwise direction. Now let's look at a little different scenario. This is the image of a steel hammer where we have an impact load, but it's not a cyclic rotating shaft. And what we have here is, here you can see a very smooth surface, and then here we have the brittle fracture. So if you remember from your 250 experiment where you pulled the tensile specimen apart, you had a very rough, jagged surface. And that's the kind of surface that you get here where we have a brittle fracture. But a fatigue surface, it propagates a crack in one usage or one rotation, and then that crack is pushed together again, then opens up a little bit, and as the cycle continues, it works itself back and forth on top of itself. And so the failure surface is usually much more smooth than a brittle fracture failure surface. And that's because as the cracks propagate, they push back and forth on each other, smoothing out the rough edges. In this case, what we had is an axial rod, and we initiated a crack here in the middle. And then as this axial load was applied, this rod propagated a crack radially out in this direction, and then you can see here that we had the final brittle fracture. Compared to the previous example, the applied load is a lot bigger in this case because we have a lot more area here that experienced brittle fracture compared to the fatigue surface. These figures here are in your textbook, and they come from ASME Metals Handbook, Volume 11. And what they do is they give a specimen that has a particular notch or is unnotched. Then they give it a high nominal stress and a low nominal stress. And they show you what the striations or the beach marks would look like in a fatigue failure. Now these plots are a little bit challenging to understand. So make sure you read through your manual and you study these long enough to understand what's going on in the plot. What I've shown down here is I've added these rectangles here. And the side view shown in the third row is a view of the plane shown in the diagram below. So look straight into the page on the shaft shown on the top row, and this is the stress distribution at the center of the shaft looking straight into the shaft. So what you do here is, this is the shaft along its length, then looking down the axis. So looking down the axis in this direction, this is the failure that we would see if we had a propagating failure stress. Then this would be the cross-section end view if we had a rectangular shaft. And then this is looking down on top. These images here also show us failure propagation modes. So what I would expect you to be able to do is, given a certain loading on a cross-section, I would expect you to be able to draw the striations or the beach marks and show how the failure due to fatigue would propagate. I would also expect you to be able to look at a failure like this and describe how it did fail, whether it was a fatigue failure, a brittle fracture, or a combination, whether the shaft was rotating or stationary, whether the loads were large or small. So make sure that you can analyze a failure and explain the failure, how it occurred, and then also be able to draw a failure and the striations and beach marks associated. We want to now look at the various theories and approaches to solving fatigue problems. There are three major fatigue life models, and these are the methods that predict the life in number of cycles to failure for specific loading. And the three life models, fatigue life models, are the stress life method, the strain life method, and the linear elastic fracture mechanics method. And I'll expect you to be able to identify the three and talk about them a little bit. The stress life method is the one that we are going to use in this class. It's the least accurate, but it gives very good results based on the complexity of the model. It's the most traditional and by far the easiest to implement. So even though the first item is least accurate, and particularly for low cycle applications, it is still accurate enough to get good evaluations of the fatigue life. It estimates the life to fracture, but does not account for crack nucleation and crack growth. And it's based on comparison to experimental test specimens. And it's mainly based on the idea of what we will call the R.R. Moore beam. The strain life method is a more detailed analysis of plastic deformation at localized regions. And several idealizations are compounded, leading to uncertainties in the results. The strain life method is used when better answers or better results are needed than with the stress life method, but a full linear elastic fracture mechanics method is not required. However, to get a good result with the strain life method is a lot more challenging, and there's a lot more places where errors can be made. Then the last method, the linear elastic fracture mechanics method, it assumes a crack exists and then it predicts the crack growth with respect to what we call a stress intensity factor. And this is the most accurate method, but it is very mathematical and complex to apply to a practical problem. So we will focus again on the stress life method, which is based on the R.R. Moore beam approach. So what happened is Moore took a round rotating specimen and he measured how long it took to have the specimen fail in fatigue. So in this method, what Moore did is he took this beam and he polished this surface right here, and he carefully machined it to a very precise size. And then he put this in a spinning machine where he could apply a moment. And he applied a bending moment to this beam, and then as it spun, it would see tension and compression and tension and compression, and then he would count the number of cycles till it failed. And what he did is he plotted this diagram where on the vertical axis here we plot what we call the fatigue strength, SF, and on the horizontal axis we plot the number of cycles to failure. And so at 10 to the 0, this curve starts at the SUT, which makes sense. If this specimen were to undergo one cycle before it ruptured and broke, that would be the ultimate strength of the material. Then, as the number of cycles increases, you can see that the fatigue strength continues to drop. Now, the black dots here represent experimental data. And we can see that there's a pretty good linear relationship up to just under 10 to the 3rd cycles, and that there's a constant line, a constant slope. Then once we hit up in this region here, we have a steeper slope that comes down, and then here we actually go flat. So what this means is that if I were to give us this particular specimen a stress of 100, I could cycle it up to this many cycles before it failed in fatigue. Now for us in this class, we're going to make this chart a little bit easier to draw. We can see here that this inflection point occurs at a number less than 1,000. But we are going to make this number 1,000 for this class. And so between 0 and 1,000, we will go from the SUT down to this inflection point here. And then from 1,000 cycles up to 1,000,000 cycles, we will have this region here. And then above 1,000,000 cycles, we see that the SN diagram goes horizontal, which means that any stress in this region here, any stress below the endurance limit, will never cause a fatigue stress. And that's actually the definition of the endurance limit. This SE here is called the endurance limit, and it's the maximum stress that can be applied such that a fatigue failure will not occur. Then if the stress goes larger than the endurance limit, then we start to limit the number of cycles that our part can live for. Now you can see up here that we have finite life, and finite life is defined as being from 0 cycles, 1 cycle, up to 10 to the 7th. We're going to move this finite life back to 10 to the 6th, and then infinite life from 10 to the 6th on up. They give this region here because there's a lot of uncertainty when we get to this number of cycles. But we will use finite life from the first cycle up to 10 to the 6th, and then infinite life from 10 to the 6th up. Low cycle fatigue is often considered in this region here up to 1,000 cycles. And then high cycle is above 1,000 cycles. You'll note that the number of cycles to failure at varying stress levels is plotted on a log-log scale. So both axes here are on a log axis. For ferrous materials, a knee occurs here. The endurance limit occurs at 10 to the 6th. For non-ferrous materials, a lot of people say there is not an endurance limit. And we will discuss that in a minute. So you need to be able to reproduce this plot, label the important regions on the plot, and be able to discuss these important values. And again, this plot was developed when Moore took his beam and he finely machined it, carefully machined it to these dimensions, and then polished this surface to make sure there were no cracks. And then he spun it with an applied moment, and when it failed, he recorded the number of cycles and the stress and plotted this line. So we're going to look at this SN diagram again, but we're going to let this straight line region here, which we're going to say occurs at 10 to the 3rd cycles up to 10 to the 6th. This is the region we are most interested in fatigue analysis. In low cycle fatigue, there are other methods that are more accurate than the Moore beam approach and the stress life approach. And then if we have an endurance limit that is, if we have a stress that's lower than our endurance limit, we won't have a fatigue failure. So this region here becomes our critical region for design. The equation of this straight line right here is given by SF is equal to AN to the B. So this is the equation for a straight line in a log-log plot. Just like y equals mx plus b on a regular plot is the equation for a straight line, SF is equal to an to the b is the equation for the straight line on a log-log plot. So SF is equal to an to the b is the equation of this straight line. If I tell you the n, you should be able to come and compute the SF, which would then give me the associated SF over here. A and B are given by these two equations. A is equal to script F SUT squared over SE. The SUT is the ultimate strength of the material. SE is the endurance limit of the material. This F is called the fatigue strength factor and comes from this table here. So on this plot, what you do is you have script F on the vertical axis, and on the horizontal axis we have the SUT in KPSI. So if we know the SUT for our material, we come to the SUT and we come up till we hit the curve, and then we come over and we pick off our little f. Now you'll note that for most steels, the little f will be between 0.8 and 0.9 SUT, or the value for point F will be between 0.8 and 0.9. So coming back now to this equation for A, given our material, we would be able to look up F from the chart. We know our SUT and we know our SE. Then we could compute A. To get B, we have minus 1/3 the log of F SUT squared over SE. And you can see that the F SUT is this upper limit on the line, and SE is this lower limit on the line. So we could come over and mark this inflection point here as F SUT. And again, the F is typically between 0.8 and 0.9. And so given our material and our endurance limit, we could compute the fatigue strength associated with a number of cycles. You will use these equations a lot in. Let's now look at the SN diagrams for other non-ferrous materials. Here we have on the vertical axis the peak alternating bending stress, and then the number of cycles on the x-axis. And what happens is these would be wrought irons, some sand cast materials, and some permanent mold materials. And you can see here why people say that there's not an endurance limit. But on the other hand, I also argue that for these wrought materials, and certainly here in some of these other materials, this line starts to go pretty flat. The inflection point might not be 10 to the 6th like it was for ferrous steel, but coming out here to 10 to the 8th and some of these higher numbers, I would argue that we have a close approximation to an endurance limit. Takeaway points are non-ferrous metals often do not have an endurance limit. Fatigue strength SF is reported as a specific number of cycles. So in order to report SF, you need to have SF at 10 to the 5th cycles, or SF at 10 to the 4th cycles. And this figure above shows typical SN diagrams for various aluminum materials as well. In our fatigue analysis in this course, we will stick with the fatigue analysis of low carbon structural steel. We now want to look at a relationship between the ultimate strength and the endurance limit. And what we can see here is a bunch of experimental data where the ultimate strength was plotted on the x-axis and the endurance limit was plotted on the vertical axis. And you can see that the endurance limit here is called SE prime. And what we see is that the experimental data kind of follows this dashed line up to a point and then goes horizontal. And so what researchers have done is they've fit these data and they say that SE prime, the endurance limit, is equal to 50% of the SUT as if the SUT is less than or equal to 200 kpsi. Then if the SUT is greater than 200 kpsi, the SE prime is simply 100 kpsi. And it doesn't increase, it holds flat. So even though our ultimate strength continues to increase, the endurance limit doesn't increase. Now, this SE prime is what we are going to call the unmodified endurance limit. And so this is the case that you would have if you had a perfect RR Moore beam that was sized and polished and loaded carefully. So SE prime is the unmodified endurance limit. And we have a relationship as given here between the unmodified endurance limit and the SUT of the material. We'll use this equation a lot in our analysis, and it's important that you can visualize and remember this information. Now what we need to do is modify our endurance limit for the particular problem at hand. And this is where Chapter 8 or Chapter 6 will be very helpful to you. That's in creating a modified endurance limit. So the endurance limit SE prime is for carefully prepared and tested specimens that follow the guidelines of the RR Moore beam. In most applications, we cannot follow those conditions. We have different loads, we have different materials, different finishes, different load applications, the temperature may be different. And so we need to be able to modify our endurance limit. And so we do that by writing our endurance limit as shown here, where SE is equal to all these modification factors times SE prime. So SE prime is the unmodified endurance limit, and it's 50% of the ultimate strength up to 200 kpsi, and then it's 100 kpsi if the ultimate strength is greater than 200 kpsi. So now we're going to focus on computing these endurance limit modification factors. And these modification factors are often referred to as the Marin factors. So the little k's here represent the Marin factors. The first one, Ka, is associated with a surface condition factor. So this would be whether the material is ground, polished, or cold drawn, or hot drawn. Kb is the size modification factor. Moore built his beam for a round rotating bar. And if we have a different geometry than that, we need to account for the size. Load, Kc is for the load modification factor. This is where if we have bending, torsion, and an axial load, how do we modify the endurance limit? The endurance limit is a strong function of temperature, and so we have a Marin factor specifically for the temperature. And Ke is a reliability factor based on the reliability we want to have in our model. And then K sub f is the miscellaneous effects modification factor. This one includes a bunch of stuff. For us, we will mainly focus it on stress concentration factor effects. And then SE prime is the rotary beam test specimen, the unmodified endurance limit, and SE is the endurance limit for the particular problem we're solving. Now what we're going to do is come and look at each one of these Marin factors individually and make sure we understand how to compute